Hi everyone, I'm Charles, and I'm really happy to present to you today our work on Tower, which is a programming language and framework for implementing data structures that work correctly in quantum superposition. This is joint work with my advisor, Michael Carbon at MIT. So why do we want to build quantum computers? There are a lot of reasons, but one of the most compelling ones is to realize the asymptotic complexity advantage that quantum algorithms actually promise. So I've put a selection of quantum algorithms on the slide here, and you can see that they solve a lot of fundamental problems like element distinctness, subset sum, closest pair, these kinds of complexity theoretic questions. And they can actually solve these problems in faster asymptotic time than the best known, or in some cases best possible, classical algorithms. Some of these are kind of miraculous. I mean, you can solve element distinctness in less than omega of n. Quite extraordinary. If you look actually at how these algorithms work, there's a lot of detail, but what I want to point out is that these algorithms actually utilize in their core a classical data structure, like a set or a dictionary, with efficient operations. For example, these three algorithms utilize a classical set with insertion and lookup that have to occur in polylogarithmic time. If that bound isn't achieved, then you don't get this quantum speedup. You've negated the point of having your quantum computer at all. So how do we even make sense of this quantum notion of data structures? To understand that, first we have to know what it means to have data that's being placed in superposition and being manipulated by a quantum computer at all. So quantum algorithms are manipulating quantum data. What is quantum data? Suppose you have classical integers, right? So you have 32-bit integers. They range from the value 0 all the way up to 2 to the 32 minus 1. What a quantum integer is a superposition of all of these integers. Well, not so all of them. You can take a number of classical integers and put them into this object called a superposition. So for example, this superposition of 0 and 1 on the bottom left there, it's simultaneously 0 and 1. The cat is alive and dead at the same time, is how you can interpret that. And you can have an arbitrary number of these integers in a superposition. What I want to draw attention to a little bit is that superpositions are characterized by some complex numbers that you put in front of these classical pieces of data. You can loosely think about them as probability weights if you're familiar with classical probabilistic reasoning. The difference is that they're complex numbers, so they have signs, and you square them and they should add up to 1. That's all a bunch of technical stuff. There's an amplitude and there's a phase associated with each one of these superpositions. An operation that you can perform on a piece of data in superposition is called measurement. And this is how you actually get information out of a quantum computer. So say you start with a superposition of 0 and 1. If you measure this superposition, you open the box and you find out whether the cat is alive or not. You get an outcome, which is either 0 or 1, with probability 1/2 each. Here, this 1/2 is derived by squaring that square root of 1/2 in that denominator. Not too important for our purposes. So that is the idea of a quantum integer. Now what about a quantum list? Well, it's the same idea. You take a classical list, which could be something like the empty list or containing 1 or a list containing 1, 2, 3. And you can take these things and also put them in superposition. Now when we put lists in superposition, what kind of operations can we perform on them? We'd like them, for the sake of these algorithms, to be the same kinds of operations you can perform in classical lists. So you can push an element to the front of a list, and the specification is that it should act uniformly across all of those lists in that superposition, right? So that superposition of empty list and list containing 1, if I push 2 onto the front of that list, it turns into the superposition of 2 and 2, 1. Hopefully that's reasonably intuitive. So then the big question for us then is, how do we implement the algorithm by implementing these data structures that they actually rely on? Classically, this is a fairly straightforward thing to do. You assume you have some notion of random access memory, then you have some linked data cells that you allocate in there, connected by pointers, and then you manipulate them through these recursive operations that traverse through these pointers. Different implementations will give you different time complexities. You can have your linked list or your balanced binary tree, the latter of which gives you that nice logarithmic time operation. Now, the reason I'm here in front of you today is that these implementations do not work on a quantum computer. And the reasons are what we're going to be talking about next. So it was actually shown in some work on algorithms that utilize the set data structure that there are specific conditions that the data structures must satisfy for them to work correctly with the algorithm. These are some pretty weird requirements. The first one is that all of the operations on that data structure have to be reversible. What I mean by reversible is that the manipulation of that data structure is a function that can be executed forward or backward. And this is a property that's required for the superposition of that data to be preserved rather than collapsed and the algorithm destroyed. The next requirement is something called history independence. I'll talk more at length about what this means, but briefly it means that an instance of a data structure, a specific set containing a specific collection of elements, must actually have a unique representation in physical memory. This requirement enables an algorithm to exhibit the correct kind of quantum interference to get that speed up. And the third requirement is that all of your data structural operations have to execute in bounded time. When I say bounded, I mean that you know a classical parameter that upper bounds the amount of time that operation is allowed to run for. This is a rather technical condition that is required if you want to take your algorithms and compile them to a hardware compatible execution model, this quantum circuit model. The problem is that to date, we don't really have any idea what kinds of data structures actually satisfy these requirements, even though algorithms are invoking them. And we certainly don't have any tools, any languages that allow us to develop new implementations that do satisfy these requirements. So that's where our contributions come in. We have 3 contributions in this work. The first one is Tower, which is a quantum language for implementing data structures. The second contribution is Boson, which is a memory allocator that works in conjunction with Tower. And the third is that we use Tower and Boson to implement the first quantum library of data structures. The key idea of Tower is that we actually achieve these reversibility and bounded time properties by defining primitive memory operations that respect them. The key idea of Boson is that we actually make all of the memory allocations in your program history independent. So let's talk about this first reversibility requirement, and let's understand why it exists. So there are actually 2 classes of fundamental operations that you can perform on quantum data in a quantum computer. Their technical terms are unitary operators and measurements, but what I'll be doing is grouping them under these irreversible and reversible operations. So the first example I'll actually discuss is a reversible operation. The push front operation that we just saw, where we added 2 onto the front of the list, as you can see, performing this operation preserves the superposition in the sense that the machine state started as a superposition and it ends up as a superposition. This is what we want. What we don't want is an alternative situation where you, for example, measure the value of a quantum list. What happens here is that the list will collapse into a classical list, right? And this operation is going to destroy the superposition, and it means your algorithm will produce the wrong results. What distinguishes these 2 things? Well, like I said, it's because the push front of operation is actually reversible. There is a reverse, it's called remove front, right? If I wanted to undo the operation of pushing 2 to the front, then I can just remove it again. Whereas measurement, physically, there's no possibility of reversing this process. In some sense, it has lost information permanently. So if we want to avoid the second bad situation, then what we're going to need is a language where all of the primitive operations you use to manipulate data structures in memory are actually reversible. And that's what we do through the language Tower. In Tower, you can implement an operation like push front in a completely reversible way. So I'll give you a short example of how a program in Tower actually executes. Suppose we start with a situation where we have a list containing the elements 1 and 2, and we want to push the element 6 onto the front of it. So here's how the code is going to go. We're going to allocate a new heap cell to store the new element that we're eventually going to concatenate onto this list. The next thing that we need to do is we want to take the old value of L, right, the input list, and we want to put that into a temporary variable so that we can then attach it to the new list that we return. To do this, we use a reversible swap operation. This is not your usual assignment operator in a classical language. It has to be reversible, right? So we can swap the values of 2 variables. Next, we're actually going to take a pair, right? X, the element we want to push onto, and then the old list, which is now stored in this temporary variable called head. And this variable node, it conceptually lives in a register still. We're going to then need to put it into quantum memory. Before we do that, actually, there is a little thing that we have to do where we need to get rid of this temporary variable called head. Remember, I said that all of the operations in the program have to be reversible. An example of a non-reversible operation is when you take a temporary variable and you just throw it out, right? Because when you get rid of a temporary variable, you can't reverse that. You can't get it back again. So in quantum computing, you solve this using an operation called uncomputation. You reverse the process that would compute head, and reversing that process resets it back to 0 so that you can get rid of it. So that's what we do next. And finally, what we'll do is we'll take this new list node that stores 6 and a pointer of to the old list, and we're going to commit that into memory, right? We're going to dereference the output variable L, and we're going to store this node in there. So you can see we're almost done, right? L now points to 6, 1, 2, and the only last thing we need to do is uncompute the variable node in the same way. And now we're actually done, right? We've achieved the result. Now, what's really cool about having a language in which all of your operations are reversible is that it doesn't actually take any effort for you to implement the remove front operation, the reverse of this, right? Because all you need to do is you can execute every single step of the program backwards. If you just follow all of the steps backward, they're all individually reversible and you get back to exactly where you started. So all functions are reversible. If there's a takeaway from this section of the talk, right, it's that we've created a language that allows a developer to implement data structure operations that are all reversible. And the way that we do this is by introducing high-level types of pointers and data like lists and integers. And we have a set of operations that allow you to perform random memory access reversibly. This is something that previously had not been achieved in quantum computing. Cool. So let's talk about the second requirement then. This one is very funky. So to give you an idea as to why we need this history independence thing, let's consider an algorithm that is manipulating sets of integers. So the algorithms that I talked about on the first slide, for example, for element distinctness, the way that they conceptually work, it's a little bit complicated, but to sum it up real quick, what they do is they create a superposition over different sets. And then they manipulate the amplitudes of that superposition such that the sets that correspond to giving you a correct answer out of the algorithm, their probabilities, their amplitudes increase. And the sets that give you an incorrect answer, their probabilities decrease. That's the whole way that they're able to achieve that speed up. Suppose that the algorithm, when it executes, constructs a set containing the elements 1 and 2. Suppose it does this on 2 different branches of the superposition. Then we want the difference between these 2 branches to be equal to 0. Now, what do I mean by difference here? That negative sign there is actually a phase, right? It's the phase minus 1. When you have 2 things in opposite phase, it's a physics experiment you're performing where you expect these 2 things to destructively interfere with each other, go to 0, and basically act as if they've never existed before. This is a quantum property that really doesn't appear in any classical programs. If S1 and S2 are supposed to denote the same set, then just looking at the equation, you kind of expect this to hold. And indeed, the algorithms that we talked about on that first slide really, really require this property. If the property doesn't hold, the algorithm can't outperform a classical algorithm. It might even give the wrong answer. So, okay, we want this property to hold. What could possibly make it not hold? Let's zoom in on this notion of what it means to have a representation of 1, 2. Suppose that we were using linked lists to implement sets, as you might classically. And suppose that on the 2 branches of the superposition, you actually have a different linked list. 1, 2 versus 2, 1. The order is different. Classically, you might say, we're just going to consider linked lists up to order, and we're going to consider them the same set. But what will actually happen on a quantum computer is that the physical representation of S1 and S2 will be different things, and you won't have this quantum interference property occur. Okay, so it seems like this is a pretty easy situation to get yourself out of, right? After all, okay, This is going to be the incorrect output. But it seems like you should be able to fix this problem by just sorting and deduplicating all of the linked lists, right? You enforce this canonical representation. Does this get us out of the woods? Well, not quite. If you zoom in a little bit more, you realize that there's actually an underlying physical implementation of these linked lists that has values for pointers and layouts in the actual concrete memory of the computer. And so we once again have a situation where the physical representations of supposedly equal data structures are not equal. Quantum interference fails to hold, and the algorithm gives the wrong answer. Okay, so it's pretty clear by this point that we actually need a relatively strong property to prevent this from happening. What we actually need is a property called history independence. History independence actually has a pretty long history. It was originally studied by privacy and cryptography researchers who are interested in thinking about how to prevent private information from leaking out of the way in which the nodes of your data structure are laid out in memory. So the definition of history independence is pretty technical here. It talks about how if you have data structures that are constructed using the same sequence of operations, then they have identical representations. I prefer to think of it as just saying, if you have two semantically equivalent data structures, the set 1, 2, then these data structures must be physically identical in their memory representation on the computer. So what we need to do to make this linked list work is we need to make it history independent. How do we do that? So here's the key observation we make. The power of quantum superposition allows us to effectively take an average of all of the possible layouts of the 1, 2 linked list. And if you think about it, the average is unique, right? So if we take a uniform superposition of all of these possible representations, we actually get a single unique representation that we can say is what S1 and S2 both are. And as a result, you will have that they are both semantically, but also physically equivalent. And the output is going to be correct. You probably have some questions at this point about how we actually manage to implement the operator that produces this superposition. That's explained in the paper. It's actually a fairly well-studied problem. And there's also more in the paper about how, well, if you notice, linked lists actually are still going to give you linear time complexity. You can use radix trees that actually get that nice logarithmic time. Cool. So in this talk, I really wanted to focus on the reversibility and history independence problems. The bounded time constraint is addressed more in the paper. To sum it up very briefly, we have a type system that actually allows you to bound the amount of times a function is allowed to recur using a classical parameter. For now, I'd like to move on to the fact that we've talked a lot about data structures in superposition, but we really haven't seen too many examples of them. And that's our third contribution, which is Ground, the first library of quantum implementations of data structures. There's a lot going on this slide, big table. So I want to focus on is that what we've done in Ground is we've implemented a set of data structures that have previously been unexplored in the literature of quantum programming languages and quantum algorithms. So this includes all of your classical structures like lists, stacks, queues, strings, and whatnot. What we've then done is we've shown that these implementations, they satisfy the assumptions that state-of-the-art quantum algorithms are making. And if you look at the complexities we're promising here, they're basically the same as the classical complexities. We've also validated these promised complexities by actually taking these programs and compiling them into concrete quantum circuits. And we've counted the number of qubits and gates needed to implement these circuits. There's a bunch more stuff in the paper that I think will be of interest to anyone who wants to try their hand at practical quantum programming. One of the big questions I had to address when I was implementing this data structure library is there are a lot of things that are very easy to implement on a classical computer that you would think translate really easily to a quantum computer, but really just don't. And there's some fundamental problems we had to overcome here. A lot of them have to do with this uncomputation phenomenon and how it interacts with the fact that your language also allows recursion. It also allows arbitrary mutation. This last point here is actually really fun. Hopefully, the paper will make it clear, but the idea here is that the way that you compute the complexity of a quantum program is really unintuitive for someone who is used to writing classical if statements and saying things like the complexity of an if statement is the maximum of the complexity of the two branches of that if. In quantum, that's typically not the case. You actually typically have to add the complexities of the branches, which is just super weird. And it makes implementations very difficult, but we managed to overcome these problems. Cool, so just to briefly recap, this work involves 3 contributions. The first is Tower, which is a language for implementing data structures that work correctly in quantum superposition and are compatible with quantum algorithms. The next is Boson, which is a memory allocator that works in conjunction with Tower to ensure that all of your data structures will be history independent and therefore give you that nice interference and speed up from those algorithms. To validate all of this, we've implemented a library of data structures and compiled them to a form that you can actually run. Speaking of running things, we have an artifact available. I would encourage anyone to check it out. I was honored to receive the Distinguished Artifact Award for this artifact, so I hope that it will be of use to you. My parting message is quantum software is going to be really difficult to build. One thing that I think we can learn from is a lot of classical principles like history independence that we may not really even be expecting. And I think these properties will actually allow us to build bridges to making quantum software that is both scalable and accessible. So let's find more of these kinds of things. That's it. Be happy to take any questions.
Thanks for the great talk. I wonder if you could go back to your slide where you show the 1/6 history independence. I guess I'm trying to understand the ramifications here. So if I had 50 qubits, then this would be 1/50 instead?
Yeah.
And does that mean that constructing an element of a data structure is always going to scale with the number of qubits?
That's a great question. I was hoping somebody would ask that because there's a really fun answer to it. So you would think that performing this thing where you take all of these superpositions is going to require really high complexity. I mean, there are in factorial different permutations, and then you have to somehow get a uniform superposition of all of them. I was really worried about this at first too, but it turns out that this is actually a really well-studied problem in quantum simulation. So when people want to simulate bosonic states, they have aggregates of bosonic particles, they want to enforce the property that when you interchange the positions of these particles, the representation of the state doesn't actually change. So quantum simulation algorithms have actually developed really sophisticated ways of implementing just this. There's a paper that came out of Google, I think, a few years ago that implements this operation in O of n log n time. And what's also really cool about this is the way our memory allocator works is it allocates new memory from a free list, right? You have your simple free list implementation. So it's sufficient to run this operation on the free list once before the program starts. Right? This creates a uniform permutation of all your free lists. And then when you actually want to allocate memory, you just pop from the front of that free list. It's constant time. Once you've done this operation once at the beginning in O of n log n time, the rest of your allocations are free.
Yeah, thanks for the great talk. Perhaps a naive question, but the complexities that you showed, you said that they're in line with the state of the art in quantum languages, but they also looked to me from a quick scan like they were similar to classical computer complexities. So question, are these classical data structures the data structures that we want to be using in quantum, or are there interesting quantum structures that exploit quantum better?
That's the million-dollar question, isn't it? I mean, I wish I had a good answer to this. I've been asking all of my algorithm, expert friends that I know. Most of the algorithms that you will run into in practice use some sort of variant of the set and dictionary data structure, I mean, with some slight variations. I've been interested a long time in whether you can actually have a truly quantum data structure that has no classical analog, and whether that's going to be able to give you additional speedups. I haven't found any. I'm going to keep looking. I hope to have an answer to that.
Okay. Any other questions? If not, let's thank Charles.